however, is going to be indicative of a place where water has really slowed down, and the turbulence, the energy of the fluid that's moving it has really slowed down. So we could be looking at a lagoon type of environment, the very deepest parts of the sea, a lake. Because the color, I want to say maybe a lake, but I don't know where this rock came from. So we're looking at places where the water has really calmed down. And a good example of how that works is by using our specialized equipment here called a sedimentator, where we have some little pebbles, we have sand, we have all sorts of mud, and of course we have water. And we could think about, and if you've played in a sandbox when you were a little kid, you're probably ahead of the curve here. If you haven't though, it's okay. But you get a sense of when you shake this, and you kind of let it, you're just moving it a little bit now, the water is still brown. And it's brown because the grains that are up in the water column are clay. They're very fine grained particles, or mud, basically, and they're still up in the water column because the water is moving sufficiently to keep them aloft. At the bottom, though, we're going to see the pebbles, we're going to see the sand. If we shook it up a bit more, we're going to lift up some of that sand, and some of that sand will be in the water column, and maybe only the pebbles are rolling around the bottom, right? So what we need, then, to get something like this very, very fine-grained, all this mud, looks a lot like the claystone actually, deposited at the bottom, is we need water to be really, really calm for a while. It actually takes several days after we shake up one of these, several days for it to completely settle down and the water to be clear. So sedimentary rocks of different grain sizes tell us about the different energies of the environment, and that's pretty special. We know that something like this probably isn't from a sandy beach, right? We know something like this is probably not from a glacier. We could really start to pinpoint some of these environments on the surface that these came from. Also wanted to point out that a lot of this weathering that we've been talking about, this sediment maturity we're going to continue to talk about, is generally something that happens to siliciclastic sediments. But I want to mention, too, that as we're looking at some of these, when we talk about fossils, when we're looking at fossils, and I have some other local rocks, we're also thinking about how the grain size, whether we have some nice big seashell fossils that are really broken up and busted, is very different from a limestone that has very fine, very delicate little fossils that are whole and complete, or a very fine, muddy shale that contains these teeny tiny little worm fossils called graptolites that would require a very delicate, very calm water, maybe in a deeper sea, in order to be deposited. Okay? So something like this with these big pieces of shells that are all broken up indicates a much more turbulent environment. Well, they're seashells, so they still have to be the ocean. We're not talking about the base of a mountain. How can we have an environment in the sea, the shallow tropical sea that we know existed here in northern Kentucky, be very turbulent? We're looking at hurricane deposits largely, so storms, because we know northern Kentucky used to be much closer to the equator. So storms would have been very common, and if you drive around, along 471, 275, especially up in Cut in the Hill, AA Highway, one of my favorite places, anywhere around Fort Thomas, Newport, you see these big bodies of gray rock. Every time you see one of those layers that contains a whole lot of busted up fossils like this, that indicates a storm deposit. These animals lived in a very turbulent environment, very nice warm tropical sea, but stormy, not too different than the Bahamas today. And you're seeing basically a mass death assemblage from a typical tropical storm. So that's kind of special, right? That tells us that we're looking at a different climate, a different paleo-latitude, a different latitude than we're experiencing today. It tells us about the life that was going on here in northern Kentucky. And we could look at that over a period of time from bottom to top, from the older rocks up to the younger rocks, and get a sense of how that habitat changed, which is, in the end, kind of the most special thing that sedimentary rocks tell us. Each one of these rocks can help us pinpoint a certain habitat, like, this is a lake, this is a river, this is a very deep sea, this is the edge of a glacier, very cool stuff. But we have layers of sediment that build up, and we know the oldest ones tend to be at the bottom. So as we go from bottom to top, we're seeing how these habitats changed over time, over a very long period of time. And we can see that in Kentucky. So I'll kind of go ahead and do that example here, where we look at how that occurs. So we have this rock that has a lot of broken up, busted pieces of shell in it, all sorts of, probably a dozen different species here. We got some brachiopods, we got some bryozoans, probably half a dozen different species. Got some Constellaria bryozoan here. Lots of cool stuff. Strophomina brachiopod. You don't need to worry about the fossils, but there's a whole lot of organisms living in the same place. Though this isn't showing you where they actually drop dead, we're looking at lots of turbulence here tossing them around. Okay, this rock also is the youngest rock that we see in northern Kentucky, with the exception of what we see out toward Florence, the Ice Age stuff with the giant ground sloths, the mastodons, the bison at Big Bone Lick State Park. That's far, far, far younger, not related to anything I'm talking about here. But this is some of the youngest limestone in the area. Now if we go to the older limestone, so we can kind of pile these up actually, we're looking at some limestone that is much more delicate. We have these little, I think these are Oniella mostly, little very delicate, thin-walled brachiopods, indicating they didn't live in a place that had a whole lot of turbulence, but either way, they died here and were covered over by sediment, and this sediment is much finer, and the shells are also not broken. So we're looking at a much less turbulent environment here of deposition. This rock is a little bit older, so we can kind of start stacking here, right? We have a shale that has nice, delicate worm fossils in it. To get any kind of worm fossils, a lot of times we find like tracks and trails and burrows. We get trilobite footprints sometimes. They're really cute. But in order for delicate things like that to be preserved, we're not looking at shallow, turbulent places that experienced lots of wave action and much less storm action. We're looking at relatively deep parts of the sea. So we're getting into deeper and deeper stuff where that sediment, I'll just grab the sedimentator over here, where this sediment is allowed to settle out and make really fine-grained stuff, So that's going to be a much calmer environment. Well, if we find rock like this, this is evidence for some of the oldest rock in northern Kentucky. So we're going from the Ordovician period, we're looking at about 450 million year old rock up through about 444 million year old rock, something like that. But then we have something very special. We're on top of this. We get rock that is younger, not here in northern Kentucky, but if we go out into eastern and western Kentucky coal fields, we start to get in Red River Gorge, where we have lots of sandstone, we get different environments. That sandstone, and I'm not going to pile this on top because it's the heaviest rock here, but sandstone like this is indicative of often river deposits. This one's actually from Utah. This is probably from an ancient desert. But we get this very cool texture, I'll talk about in a little bit, called cross-bedding, that happens in Red River Gorge, also indicative of river environments. As Red River Gorge is now, it was also about 300 million years ago. We also have that red sandstone from river deposits throughout eastern and western Kentucky, and would have been here, but it's all eroded, and we don't have it anymore. Interbedded with coal, because those rivers, still relatively close to the equator, would have had back swamps and kind of tropical areas and swamps, lots and lots of plant material, compressing, decaying to an extent, but not all the way, is going to form beds of coal. So we have our old, very deep sea sediments. We're getting progressively younger, but most importantly, we're also getting more shallow, into more turbulent environments as we go higher up in the northern Kentucky area. And as we get into younger and younger rock elsewhere, we're getting into beds of sandstone and coal that indicate terrestrial environments. We're looking at rivers with swamps. So we're looking at a whole 100 to 200 or so million year old story of sea level change in Kentucky. And we see these records of sea level drop, sea level rise all throughout the rock record. And it's very special because it correlates to climate fluctuations and helps us to understand what kind of things have caused climate change in the past, what kind of things, and we could use the past to help us understand the present, which is very special. So what's sea level doing then? If we're going from deep sea to shallow and then finally terrestrial environments, what do we think? In the same area, one space, one spot, sea level going from deeper to shallower, then finally landward environments. We're looking at sea level dropping, okay? So, and not a surprise because Kentucky is now, well above sea level, but that's a very special story to be able to tell. So looking at a package or a sequence of sedimentary rocks gives us a whole bunch of information, way more than any individual rock could. But we have to understand what the individual rocks tell us in order to make sense of a whole series of strata. So that's very special. I'm going to back up, though, and get back into weathering. That was just kind of a segue as we talked about energy levels and how we can use, oh, I shook the wrong one, huh? I want to keep it, that's fine. You kind of understand that. I'm good with that. So I want to move on to what's happening as we're weathering different kinds of rocks. We're looking at the maturity of a sediment. We talked about textural maturity a bit. We've got our big, gravelly, angular chunks. We're moving to finer and finer, better rounded, better sorted